Okay, so I finished doing the calculations for the x and y components. This is what we got, and here's it written out in unit vector notation. And then the calculations for the x and y components for b. Now, one thing we have to be really careful of is sign. From the diagram, we can tell that the y component is pointed down along the negative y-axis. This vector is pointed down, so we need to throw in a negative sign there. We always want to check and make sure that we've got that sign right, because depending on how we got the angle, our calculator might spit out a positive or negative answer, and that might not be correct. So we always have to check the sign. Anyway, in unit vector notation, this is what we get for B. And since we're trying to find C, we'll write this out. So what colors can I use? So for C, we're going to have Cx is equal to Ax. The x component of C is equal to the x component of A plus the x component of B. And looking at that, the x component of A is right here. That's 49.6. And the x component of B is 86. And we can get the y component. With the y component of A, which is 136.3. Oops. And then the y component of B was negative, so that's negative 60.2 meters. So you get 135.6. And 76.1. So to find the magnitude of C, we can put this all together. So we've got 135.6 meters I hat plus 76.1 meters j hat. Magnitude of C we're going to get from Pythagorean's theorem. And the angle we're going to get from the arctangent. Okay. All right, so 155.5 and 29.3 degrees. All right, let's try another example. Same thing, we've got two vector, or actually in this case, sorry, we've got three vectors we're going to add together, A, B, and C, and the resultant. Now, the thing that's a little bit strange in this case is we know the resultant, it lies on the x-axis and has a magnitude of 35. We know our first two vectors, and we're trying to figure out what value and direction for C should it be so that we do get a vector that's perfectly horizontal and has a magnitude of 35. So here's how we're going to do this. We set this up. Think of this as a basic algebraic expression where we've got a plus b plus c equals r, and you were given the value of a and b and r, and we need to find c. Well, what we can do then is we just need to figure out what's missing, and solve. So this is how we would solve the problem with scalars, and the way we solve it with vectors is very similar. It's just a little bit more involved, that's all. So again, the first thing that we're going to do is we're going to set up all of these vectors as unit vector notation. So we're going to go with A here. The angle is 60 degrees. And here's our vectors A. Okay. So our x component is adjacent, so that's going to be cosine. So we're going to have, and what's the magnitude of A? Oh, 20 meters. Okay, so we're going to have 20 cosine 60 degrees, and then the vertical component's going to be sine. So we'll have 20.0 meters sine 60 degrees. And then for B is exactly along the horizontal. So that means that it has no component in the y. So it's 0 meters j hat, and all in the x, the positive x direction. Okay. Now C is unknown, so what we're going to do is we're going to write placeholder variables. We'll just write Cx, Cy. And then again, R is perfectly horizontal, so it's got 35 meters in the x direction and nothing vertical, so 0 meters j hat. We can set up a scalar equation now by taking this box and this box. For this box to work, we would need to have ax plus bx, that's these components here, plus cx equals rx. So can you see how this is similar to that scalar, real simple algebra problem we were just looking at before? Okay, so we've got 20 cosine 60. Now, cosine of 60 is one of our special right triangles, so we should have that memorized. And I think that's 1/2, so that's going to be 10. So we're going to have 10 meters plus 10 meters plus cx needs to be equal to 35 meters. So it looks like cx needs to be 15. That agrees with our diagram that the x component of c should be in the positive x direction. We're expecting the y component of c to be in the negative y direction, so we'll see what happens. That's 15 meters. Let's see what happens over here. So this is not as easy, right? Sine of 60 is what is that? Root 3 over 2. So we'll have 10 meters, 10 root 3 meters. Plus 0 meters plus cy needs to be equal to 0 meters. So we can see the solution to this is pretty straightforward. Let's write this out for clarity. Okay, so it looks like cy needs to be negative 10 root 3 meters. So now we know what c is. 15 meters I hat minus 10 root 3 meters j hat. We can find the magnitude of c using Pythagorean's theorem. Now, don't mess this up in your calculator by forgetting to put the negative sign inside the square, right? Got to square the whole thing. So there you go. And when we put that into the calculator, we're going to get something close to 22.9 meters. And our theta tan, arctan, we're going to have negative 10 root 3 over 15. And our calculator is going to spit out negative 49.1 degrees. Now, whenever we use arctan, we really should be checking to make sure that the angle is correct, because the arctrig functions in your calculator will only ever give you angles in the first and fourth quadrant. So if our direction is supposed to be in a different quadrant, it's not going to be correct. So just from looking at that diagram, here's C down and to the right. So C should be like this. This angle here, that is negative 49.1 degrees. So that's correct. We would know it was incorrect if, like, say our diagram gave us a vector that was pointed up here in quadrant 2, then we would know, well, we need to add 180 degrees to get the answer from the calculator to match our diagram. That's one of the reasons we always have to draw diagrams, because the calculator could give us an answer that's not valid. All right, so that's that. You guys try out the homework today and tomorrow, and if you have any questions, let me know.